In this lecture, we are going to study statistical factor models. Statistical factor models are an example of unsupervised learning. This is very different from the models we discussed earlier in the course. Earlier in the course, we looked at models such as ARIMA, where the goal was to make an accurate prediction. We knew that the predictions were accurate when they were close to the targets. One way to picture this is, you have your data X and you have your targets Y. Your model outputs Y hat. And your goal is to find the parameters of your model so that Y hat is close to Y. So you can think of the box that goes from X to Y as the real-world phenomena that maps the input to the output. Your goal is to model this real-world phenomena such that your model's output is close to what happens in the real world. Okay, so we call this supervised learning. But unsupervised learning is different. Again, we can use a picture. In unsupervised learning, we say that it's unsupervised because we are not given any targets. There is no supervision or teacher in that sense. All we have is X. But we are still trying to make a prediction. In our picture, there is some hidden variable Z that we are trying to predict. The way that Z and X are related is this. Z and X are related through real-world phenomena. But instead of X going to Z, Z goes to X. So before we had X going to Y, so X was the starting point. In this case, X is not the starting point, but rather the end point. Z is the starting point. We call Z the hidden cause or the latent factor because it's something that we can't see that is causing the data that we observe. An example of this is when you go to the doctor. You go to the doctor because you have symptoms, which are things that you can observe. But you don't know the hidden cause, so the cause is hidden. You hope that the doctor will choose the right hidden cause so that you can be treated appropriately. So what happens when we build a model to predict Z? For the sake of this picture, we'll call the predictions Z hat. Well, it's the same idea as with supervised learning. We want Z hat to be close to Z. That is, we want to build a model that accurately reflects the real-world phenomena. Of course, the problem is we never actually get to observe Z because it's hidden. The only data we observe is X. In any case, this is just a very high-level description of unsupervised learning. In the rest of this lecture, we will look at more specific methods to actually build models that take us from X to Z hat. The specific technique we'll use in this lecture is called principal components analysis. And just as a side note, since we never actually get to observe Z, we're going to conflate Z with Z hat and just call our model predictions as Z without any hat. It should be understood that these are predictions. Let's first motivate this problem by starting with the CAPM. The CAPM says that all stock returns are linearly related to a single factor, which is the market return. Beyond this, there may be some noise, which makes it so that the returns on any particular stock do not exactly track the market. But as we stated earlier, the CAPM is what we call a single factor model. There are other models where stock returns can depend on multiple factors. One example of that is the Fama and French three-factor model. And in this lecture, we are going to study statistical factor models. In these models, we assume that we can never directly observe the factors, and instead, we treat them as hidden causes. Let's look more closely at the form of this factor model. The factor model can be stated as follows. It says that the return for stock I at time t is a linear combination of k different factors at time t. We use the letter Z for these factors, so we have Z1, Z2, Z3, all the way up to Zk. For now, we'll call the coefficients for these factors beta so that they correspond to the financial beta we discussed earlier. Okay, so hopefully this is pretty intuitive. It's exactly like the CAPM, except that we have more factors, and also, we do not observe these factors directly. Let's think intuitively about how we can find these factors. Consider this scatter plot of two highly correlated variables, height and weight. Generally speaking, the taller you are, the more you will weigh. Of course, there are always exceptions, like very tall and very skinny people, or very short and very fat people. But we expect that most people will generally lie somewhere in the middle, so you get this kind of strong correlation. From this, it's clear that there is only one single factor that controls both of these observed variables. What is this factor? Well, we might think of it as size. So the single size factor controls both your height and weight. The physical manifestation of this might be a specific gene. Let's suppose that the average person like you and me cannot directly observe genes, so for all intents and purposes, genes are hidden. That means there is a hidden variable called size, and this is causing the height and weight of an individual to be either smaller or larger. The key trick in principal components analysis is rotation and variance. Let's suppose that we rotate the axes to align with the height and weight scatterplot. Equivalently, we can think of rotating the data points themselves. Now, what can we see? What I want you to notice here is the key principle behind PCA. It's that in one direction or one axis, there is a large variance. For this picture, I've chosen the horizontal axis to be this axis with large variance. In the other direction, there is a very small variance. It should be clear that this direction of large variance corresponds to the hidden factor we're calling size. This direction is called the first principal component, denoted by the unit vector z1. The second principal component, which has less variance, is denoted by z2. You can imagine sort of sliding a point along these dots. At the far left end, we have a small size, which corresponds to low weight and low height. At the far right end, we have large size, which corresponds to high weight and high height. In other words, this single variable controls both height and weight. Now, in reality, you're going to have hundreds or thousands of dimensions. So the previous picture you saw where we go from 2 dimensions to 1 dimension is just for intuition. In practice, we might go from 2,000 dimensions to 5 dimensions or 2 dimensions. So the savings we get by transforming our data can actually be orders of magnitude. The best example for this in this class is obviously stock returns. So we have about 500 stock returns, but we know that they are not independent. They have correlation. We discovered this when we learned about portfolio theory. And as you know, when we have correlation, this is a good opportunity to use PCA, which again stands for Principal Components Analysis. So here's how we are going to approach these lectures. In the rest of this lecture, I'm going to show you how to use PCA in code. We'll also talk a little bit about what it's actually doing and how to make use of the outputs. This will help you relate the code to the equation for the factor model that you saw earlier. Now, this lecture is not meant to be in-depth, but to just give you a very high-level overview of what's going on. This is what I'll refer to as the beginner lecture. In the next lecture, which I'll refer to as the intermediate lecture, I'll discuss what PCA is actually doing mathematically and how it can be applied. There are some very interesting applications of PCA, such as visualization, denoising, and decorrelation. But of course, to understand that, you have to understand the math. Note that if you don't have a strong background in math, then you may consider the following lectures optional and skip straight to the code. The following lecture will be the advanced lecture. The advanced lecture will prove to you that PCA actually does all the things that I've claimed it can do. Again, this one is optional, so if you are a beginner, don't feel like you are required to watch it. These lectures will help you understand what we are doing in the code, but you can still do the code without that understanding. Okay, so without further ado, let's talk about the code. Since we're just going to use scikit-learn, it's still 3 very simple lines of code. But it's important to know what these lines are doing and what the inputs and outputs are. Okay, so as usual, we're going to start by instantiating a model. This time it's an object of type PCA. The next step is to fit the model. Remember that since this is unsupervised learning, there's no target that we call y. All we pass into the fit function is x. So what is x? X should be a 2-dimensional array where we have different dates along the rows and different stocks along the columns. Remember that the columns in machine learning are what we refer to as features, and this is what we are trying to find the factors for. For example, Apple and Google may be highly correlated and controlled by a single factor. So that's the kind of thing that we want our model to find. Okay, so the next step is to call the transform function. So in PCA and other similar models, we don't say that we're making predictions, but rather doing transformations. This makes sense in the context of the picture that you saw earlier. As you recall, what we did was we rotated the data. Rotation is a kind of transformation. So it's not prediction per se, although it can be thought of like a prediction. Finally, note that often the fit and the transform functions are conveniently made available as a single combined function, simply called fit transform. So if you want, you can do both of the previous steps in just a single line. Okay, so what's this output Z? Well, if we think of the input X as an n by d matrix of features, we can think of Z as an n by k matrix of transformed features. Note that they have the same number of rows because they both must have the same number of samples. In our case, that would be the stock returns for a given date and the factors for a given date. However, D is different from K. In our case, D is the number of original stocks and K is the number of factors. Okay, so there are still more details that we don't understand. One thing that's probably pretty confusing is this. Earlier, I said that the factor model is where we have the return, which we will now call x, as a linear function of the factors, which we will call z. But our model seems to do the opposite. The model takes in x and gives us z. That's what we get when we call model.transform. So why does this appear to be backwards? Why are we going from x to z instead of z to x? In fact, to understand this, we have to understand rotation. So earlier in this lecture, I talked about rotating the height and weight variables so that they live on new axes. But how do we rotate feature vectors mathematically? I claim that the mechanism to rotate vectors is by doing matrix multiplication. So why does this make sense? Well, I encourage you to try it yourself. Make up any vector and make up any matrix. Draw the vector on a piece of paper. Then multiply the matrix by the vector. You should end up with a new vector. Draw the new vector on the same piece of paper. You should observe that the new vector both rotates and stretches the original vector. That is, the new vector is now pointing in a different direction and has a different length. Now, it turns out that for PCA, the matrices that we use will not stretch the original vectors and only rotate them. I'm going to say that without proving it, but if you want to learn more, you're encouraged to inquire about my in-depth discussions on these topics. Just ask me about it on the Q&A. Okay, and so basically what it boils down to is that if we have some feature vector of stock returns called x, and we multiply it by a matrix called Q transpose, we get the vector of factors called z. Of course, when we call the fit function in scikit-learn, that's how we actually determine what the matrix Q should be. Now it also turns out that if we multiply the factor vector z by q, we get back the original vector of stock returns called x. So this is a two-way transformation. When we want to go from x to z, we multiply by q transpose. When we want to go from z to x, we multiply by q. Okay, so our goal right now is to get back to what we started with. That is, a factor model where we have a single stock return being a linear combination of factors. So far, we know that x is equal to q times z. But let's see what happens if we write this out explicitly in terms of their components. Remember, I'm only interested in a single stock. So let's say I'm interested in x1. I can see that x1 is equal to q11 times z1 plus q12 times z2. Now let's say I'm interested in x2. x2 is equal to q21 times z1 plus q22 times z2. This is just by the rules of matrix multiplication. So what do we see? We see that x1, the stock return for asset 1, is just a linear combination of the factors z1 and z2. It's weighted by the coefficients q11 and q12. we can make a similar statement about x2. Okay, so hopefully now you are convinced that this implements the factor model we discussed at the beginning of this lecture. It's simply that by doing matrix and vector multiplication, we can calculate the returns for each stock simultaneously. That is, we get x1 and x2 at the same time in one operation. So if you want to think of the factor model I described earlier in terms of betas, you can just imagine that a bunch of those are being calculated in parallel.